The last thing we want to look at to finish up section 11.1 are increasing and decreasing sequences and sort of the consequences of those. Okay, so a sequence is called increasing if every term is less than the term that comes after it. Okay, so it has to be strictly less than the term that comes after it. So in a sequence like 2, 4, 6, 8, 10, etc., 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 would be increasing because 2 is less than 4, 4 is less than 8, 8 is less than 10, 10 is less than 12. Okay, so that's increasing. Decreasing is if every term is greater than the one that's after it. Okay, and so if we were doing, 100, 99, 98, 97, like each term is larger than the one that came before, that comes after it. Okay, and then we call a sequence monotonic if it's either increasing or decreasing. So mono is like 1, so it has like a sort of one thing that it's doing, one tone. It's either always going up or it's always going down, one or the other. So it could be, if I have an increasing sequence, I would call that monotonic. If I have a decreasing sequence, I'd also call it monotonic. Okay, so it's monotonic if it's just always trending in the same direction. Okay, so some examples to show if a certain particular sequence is decreasing. Well, to show that a sequence is decreasing, we just need to show that a sub n is greater than a sub 1 for all n greater than or equal to 1. Okay, so let's look, or sorry, that should have been n plus 1. All right, so a sub n would be 3 over n plus 5. And a n plus 1 would be 3 over n plus 1 plus 5. Okay. And we want to compare these two and ask ourselves, is that actually greater than? So this is 3 over n plus 5, and this is 3 over n plus 6. Okay. So the question is 3 over n plus 5 greater than 3 over n plus 6? Well, yes, it always has to be true. So for all values of n greater than or equal to 1, the denominator here will be larger than the denominator here. And so since this denominator is larger, this fraction will be smaller and this fraction will be bigger. So 3 over n plus 5 is indeed greater than 3 over n plus 6 for all n greater than or equal to 1. Okay, so it's decreasing. All right, let's try another one of those. All right, so once again, if I'm trying to show that it's decreasing, I just need to show that the nth term is greater than the n plus first term. So let's look at the nth term. The nth term is just n over n squared plus 1. And then let's look at the n plus first term. That would be n plus 1. I'm just substituting n plus 1 here, and here, and here. So n plus 1 over n plus 1 squared plus 1. Okay. And then I'm trying to ask myself, well, is that relationship true? All right, and let's expand that out. So, of course, this is just n over n squared plus 1. This is n plus 1 over, and this will be n squared plus 2n plus 1, and then plus 1. Okay, well, up here we had the same numerators, so we just really had to look at the denominators, but here the numerators aren't the same, so we can't make quite that simple of an argument, but we could cross multiply basically. So I can multiply both sides by this, and by, multiply these two, and multiply these two, and see if this product is greater than that product. Okay, so this is really n squared plus 2n plus 2, so I want to see is n times n squared plus 2n plus 2, is that greater than n plus 1 times n squared plus 1? If so, then this fraction has to be larger than that one. Okay, so this one, when I multiply it out, I'm going to get n cubed plus 2n squared plus 2n. I want to know if that one's bigger than, okay, so here I'm going to get n cubed and then plus n squared. So that takes care of this one with both of these, and I need to do the 1 with both of these, so plus n plus 1. Okay, so if I subtract n cubed from both sides, that'll go away. And then if I subtract n squared, I'll have just n squared. If I subtract n, I'll have just n. And the question is that greater than 1? Well, yes. N squared plus n is greater than 1 for all n greater than or equal to 1. Because this is just staying 1. When this is 1, this will be 2. And then as this gets larger and larger, this side is just growing, and this side is just staying 1. So this is always true. Okay. So a sub n is greater than a sub n plus 1. And the sequence is decreasing. Okay. All right, next we have the idea of a sequence that is bounded. So a sequence is bounded above if there's a number m such that every single term in the sequence is always less than m. Okay. Now this could maybe be a limit as it's approaching. Okay, but if it but it could be even something larger than that. But yeah, it's bounded if all of them. So it can't be something, you know, let's say here's m. It can't be, so here that, okay, has a limit of n, but it's not bounded above. Okay, yes, over here, sorry, yes, over here, it's a m is always bigger than these values, but down here it's not, because it took a while for it to settle. Okay, so this would not be bounded, even though it has a limit of L. Okay, so what we're talking about is that every single value, like here's m, and it goes like this, and every single value is always less than m. So this one would be an example of bounded above. Okay, by m. Okay, so all of them have to be less than. And then a sequence is bounded below. Okay, and that one would be if there's a value that it's less than, so it kind of maybe here's m down here. Okay, and it's getting smaller and smaller, but it's always above m, or m is always less than the values in the sequence. Okay. And so if we have a sequence that's both bounded above and below, then it's called bounded, just plain old bounded. So there's three different things. Bounded above, okay, like this one that I've drawn would be bounded above, but if it goes infinitely like this way, it's not bounded below. This one right here, this one's bounded below, but if it's like this, it's not bounded above. So bounded would be there's an m here and there's an m down here, and I have something that just kind of stays in between, okay, and it's always below m and it's always above lowercase m. It's always in between, so that would be bounded. Okay. So one thing to notice is that not every bounded sequence is convergent. So for instance, if we have that -1 to the end that just oscillates between -1 and 1, well, that's bounded above by 1, and it's bounded below by -1, so it's bounded, but it's not convergent. Okay. Also, not every monotonic sequence is convergent. So a monotonic sequence like a sub n equals n, like 1, 2, 3, 4, 5, 6. Okay, so that is clearly just getting larger and larger and larger. The limit goes to infinity. It is constantly increasing, and so, but it's not, so it's not convergent. But if you put these two things together, so if we have a sequence that's both bounded and monotonic, then it will be convergent. So individually by themselves doesn't tell us anything, but if you put them both together, that's very powerful. This is called the monotonic sequence theorem. So if you think about it, okay, if it's bounded, that means it never gets larger than m, it never gets smaller than m, and it's monotonic, which means the values are always getting bigger, or the values are always getting smaller. Okay, so if the values are always getting larger, well, they can never get larger than m. Okay, so then it would be convergent, and it's probably convergent to m. If they were always getting smaller, then they would be, it's bounded. They're getting smaller and smaller and smaller and smaller and smaller and smaller, but they can never be any smaller than m. And so once again, it's going to be convergent. It's going to converge to m, lowercase m. Okay, so that's a very powerful theorem as well. Okay, the last thing we want to do is look at the sequence that's defined by a recurrence relation. And this is a tricky problem because if we want to prove things, we don't have a function, a formula written out like we do for all the previous ones. So if we're going to prove anything about a sequence that's defined by a recurrence relation, we're going to need to do an induction proof. So recall we did induction proofs when we talked about sums and sigma notation. So that's really the way that we have to think about any sequence that's defined by a recurrence relation as well. We have to use induction to prove things about it. Okay. So first of all, this is going to be kind of a long example. You can see I gave you 2 pages to work it out, so we have a lot of things to look at with this one. So we're just kind of investigating this and looking at, is it convergent, divergent, what can we say about it? So, because it's defined by a recurrence relation, it has a base case here that the first term of the sequence is 2, and then it has a recursive rule. If I want to find a value in the after 1, okay, so if I want to find the second one, I'd have to put n equals 1 into this recursive definition here, and I could find a sub 2 by substituting 1 in here. So a sub 2 would be 1/2 of a sub 1 plus 6. So we know that a sub 1 equals 2. A sub 2 would be 1/2 of a sub 1, which is 2, plus 6. So 1/2 of 8 is 4. And then a sub 3. Okay, well, a sub 3, I would have to use this rule. That's going to be 1/2 of, well, a sub 2, which is 4, plus 6. So that one's going to be 5. To get the fourth one, I have to do 1/2 of a sub 3, which is 5, plus 6. So that's 11/2, or I'll write that as 5.5. And then a sub 5 is going to be 1/2 of that 5.5 plus 6. That's going to be 5.75. Okay. And I'll just tell you what A6, A7, A8, A9 are if we were to figure them out. So A6 is 5.875, A7 is 5.9375, A sub 8 is 5.96875, and A sub 9 is 5.984375. Okay. And so if you look at this and you had to guess, you might say this looks like it might be a convergent sequence because these values are getting bigger. Okay, and it seems like they're, it's not able to reach 6. So it appears or seems to be approaching 6. Okay. Now, that's not a proof, that's just I did some preliminary investigation and it seems like that's what's happening. Also, as if we look at the values 2, 4, 5, 5.5, 5.75, 5, it seems like it's increasing. Okay, but I've only looked at, 9 terms in the sequence. It's not a proof. That's just like so far, I've observed that it's been increasing for all these time, but that doesn't mean it continues to. Okay, that is definitely not a proof. These are just our preliminary observations. Okay. So if I want to actually prove that the limit is 6 and I want to prove that's increasing, I need to go to the definitions of those things and I have to actually do a proof. Okay, so let's look at the proof that it's increasing first. Okay, so this is the first thing we'll do, is that prove that this sequence A sub n is increasing. Okay. And as I already mentioned, whenever we have a sequence defined by a recurrence relation and we need to do a proof with it, the most natural way and easiest way to do it is by induction. Okay, the proof will be by induction on n. So the proof is by induction on n. Okay, and if you will recall, with induction proofs, we always have to start with a base case. Okay, so the base case is when n equals 1. Okay, so when n equals 1, we have a sub n plus 1. And we want to compare that to a sub n. Okay, and for it to be increasing, then a sub n would need to be less than. So that's the question that we have to ask ourselves. Okay, so a sub n plus 1, when n equals 1, well, this is a sub 2. Is that bigger than a sub 1? Well, yes, 4 is greater than 2. Okay, so it's true for n equals 1, which is our base case. All right, so we've established that it's true for the base case. And then we have our inductive hypothesis. Okay, in our inductive hypothesis, we're going to assume that a sub k plus 1 is greater than a sub k for some k greater than or equal to 1. Okay. And then our inductive step, okay, we have to show that it's true for k plus 1. Okay, and so in particular, we'd have to show that if we put, it's Okay, so in particular, we want to show that a sub k plus 2 has to be greater than a sub k plus 1. Okay. So this, if we can get this, then we can take this along with our base case. So we know, well, if it's true for 1, and this says, well, if it's true for 1, then it has to be true for 2. And if it's true for 2, it has to be true for 3. And if it's true for 3, it has to be true for 4, and so on and so forth. So the base case and the inductive hypothesis together give us the power to prove it true for every value of n greater than or equal to 1. Okay, so we know that from our inductive hypothesis that a sub k plus 1 is greater than a sub k by the inductive hypothesis. Okay. And so what is a sub k plus 1? Well, that is just 1/2 of a sub k plus 6. And what is a sub k? It's, well, we just want to prove that it's greater than a sub k. Okay. Okay. And so this is what we want to show. Okay. Or, well, I guess we already know this. Sorry. Okay, so we know that a sub k plus 1 is greater than a sub k by the inductive hypothesis. Okay, and so if we think about a sub k plus 1, it's this, 1/2 of a sub k plus 6. Now, I have an a sub k plus 1 here. Okay, and so if I want to show that it's less than a sub k plus 2. So to turn it into a place that I can substitute for a sub k plus 1, what I need to do is like turn it into an expression that looks like this. Okay. Okay. So in order to be able to do that, I'm just going to put this in a little cloud. Okay. Think about this. Okay, so how could I turn this side, a sub k, into looking like a sub k plus 1? Well, if I take this side and I take a sub k and I add 6 to it, and then I multiply that by 1/2, it will turn this side into a sub k plus 1. Well, whatever I do to this side of the inequality has to be done to this side as well. So over here on this side, I'm going to take a sub k plus 1. I'm going to add 6, and then I'm going to multiply it by 1/2. Okay. Okay, so all I did is take this that I knew by the inductive hypothesis, and then I doctored it up a little bit, thinking of, well, how could I turn this into that? Okay, and then whatever I did to this side, I have to do to that side. So now that we have that, okay, this one is a sub k plus 1, because I turned it into that. And if we go back to our definition here, okay, 1/2 of a sub k plus 1 plus 6 would be, I just add 1 to the subscript. So this thing is the same thing as a sub k plus 2. And so, just thinking about how I can turn a sub k into a sub k plus 1 allowed me to get that a sub k plus 2 is greater than a sub k plus 1. So that's what I was trying to show. Okay, and so now I have the base case. It's true when n equals 1. And now I have the inductive stuff. If it's true for k, then it's true for k plus 1. Okay, so it is true for 1. Okay, so these part together shows me that it has to be true for 2. Well, if it's, and then it says if it's true for 2, it's true for 3. If it's true for 3, it's true for 4, right? And so that's the power of induction, is that we know. So therefore, by the principle of mathematical induction, okay, a sub n is increasing, okay, for all n greater than or equal to 1. All right, so that takes care of the fact that it's increasing, and since it's increasing, it's monotonic. So it's monotonic by definition. Because monotonic means either increasing or decreasing. Okay, so it seems like it's increasing, and sure enough, we proved that it was increasing. All right, and then the last thing that we have to do is show that it has a limit of 6. Okay, and so let's show that it's bounded above by 6. We're going to show that it's less than 6 for all n greater than or equal to 1. Okay, so once again, we're going to do this by induction. So our base case, okay, when n equals 1, a sub 1, which is 1, is less than 6. So it's true for our base case of n equals 1. Okay, and then our inductive hypothesis, okay, assume that a sub k is less than 6 for some k that's bigger than or equal to 1, and then we want to prove that it's true for a sub k plus 1, that's also, okay, listen. Okay, well, we know that a sub k is less than 6 by the inductive hypothesis. Okay. And just like we did before, we're going to say, all right, well, what about, how could I turn this a sub k into k plus 1? Well, I know that if I take a sub k and add 6 to it and then multiply it by a half, that'll turn that into a sub k plus 1. But if I did that to this side, I have to do it to the other side as well. So I have to take 6, add 6 to that, and then multiply that by a half. Okay. Well, 1/2 of a sub k plus 6, that's a sub k plus 1. And then half of 6 plus 6, that's half of 12 is 6. Okay, so if this is true, a sub k is less than 6, then a sub k plus 1 also has to be less than 6. Okay. All right, so our base case and our inductive step here together tell us that a sub n has to be less than 6 for all values of n greater than or equal to 1. Okay. And then this is just by principle of mathematical induction. Okay. So, we know that it's increasing from this page. Okay, and now this tells us that it is bounded. Okay, so it's less than 6, so it's bounded above, and also clearly you can see that we're adding a positive, so we're taking a positive number, adding a positive number, and multiplying by a positive number, and so it always has to stay, so a sub n is always between 6 and 0. Okay, and so it's bounded. And now we know that just being increasing, that's not enough to tell us anything. But the fact that it's increasing and bounded tells us that it's convergent. Okay, so the sequence is convergent. Because it's both, okay, bounded and monotonic. Okay. And then the last thing we might want to look at is, sure, it's always less than 6, but is that actually the limit? So let's look at the limit as n approaches infinity of a sub n plus 1. Okay, which is like using our recursive rule right here. Well, the limit as n approaches infinity of a sub n plus 1 is the same thing as the limit as n approaches infinity. Well, a sub n plus 1 is really just 1/2 of a sub n plus 6. Okay. So, oops. Sorry, my phone rang. And so what we have here now is we know that it's bounded and monotonic, and so we know it's convergent. So we know that the limit as n approaches infinity of that value is some, so it has a limit because it's convergent. Okay. So we'll just substitute that with L, and then over here, this is going to be the limit as n approaches infinity, and then I can pull the 1/2 outside, a sub n plus the limit as n approaches infinity of 6. Okay, well, of course, this is just 6. Okay, and the limit as n approaches infinity of a sub n, well, it's a bounded monotonic sequence, and so, okay, it is convergent and it converges to L. So this is L. So we have that L equals 1/2 of L plus 6. So we can figure out what the limit is by just solving that equation. Okay, so if I subtract a 1/2 L from both sides, I get 1/2. Oops, I forgot to distribute. This should have been a 3. Because this is 1/2 and this should have been a 3, and that goes to 3. So this will be 1/2 L equals 3, multiply both sides by 2, and I get L equals 6. Okay. All right, so not only is it bounded above by 6, but that is actually its limit as well. Alrighty. All right. So this was probably the most involved example because of the induction proofs. So you might have to spend a little bit of extra time on any problems that require induction because it's been a little bit of time since we did that.